So you want to deploy an API for a large language model, and you're wondering which GPU gives the fastest responses and which gives the lowest cost per token generated. In this video, I'll explain the main factors influencing speed and cost, namely VRAM, flops, bandwidth, and quantization. I'll then test side by side 4 of the best known inference engines. That's the software that allows you to set up an API. Namely, I'll compare vLLM, TGI, SGLang, and Nvidia NIM. Finally, I'll compare the costs of running Llama 8B, 70B, and 405B models on different GPUs, the A40, A6000, A100, and H100. By the end of the video, you should understand how to pick the best GPU and software library for your application. We're going to cover a few things, starting off with quality and quantization. I want to describe how different data types affect the quality. Basically, I'll say that 8 bits and larger is going to be good quality, and lower, you're going to start degrading. Then I'll talk about how using these more compact, so like 8-bit or 4-bit data types, can speed up inference. And I'll talk about the details of how that works, because there is quite a bit of nuance. Then I'll go through my comparison of the different softwares, vLLM, TGI, SGLang, and NIM. I'll do that with a single prompt and also with a batch size of 64, which is kind of more representative of production. And then I'll talk about the cost per million tokens on the fastest inference software, which I've found to be SGLang. And I'll do that on 4 GPUs, and I'll do it on the Llama models of 3 sizes. Now, something I'm not going to talk about today is doing inference in a serverless environment. This is where you have GPUs scale up and turn on and then turn off if you're not going to use them. I've made a video on that before, so you can check it out right here. The first thing to understand on getting fast inference is the effect of quantization on quality. So we'll talk about how quality is affected by data type, and then we'll talk about how speed is affected by data type, because ideally we would like speed and quality, but inherently there's going to be a trade-off where we can trade off speed against quality. So to understand quantization and data types, it's helpful to review how numbers are represented. And I know this is basic, but I needed it to understand how quality and quantization are related. So let's take the number 15. In digital, that would be 1.5 by 10 to the 1. But computers work with binary, so the number would be represented, well, you could represent it in integer format, but if you want to represent it in like scientific notation with what's called a mantissa, it's like a front number for precision, and an exponent, which kind of captures the range. In binary, it would look like this. And the way binary works is this 1 here is really 2 to the power of 0. This 0.1 is 2 to the power of -1. This is 2 to the power minus 2, 2 to the power minus 3. So actually this is 1.875 multiplied by 2 to the power of 3, which is 8. And if you multiply 1.875 by 8, you get 15. Actually, if you want to convince yourself, you can ask ChatGPT. Here's how you convert this to 1.875, and then 1 is 3 in binary. So 2 to the power 3 is 8, and here is the multiplication. The way that numbers are represented then, they're stored. So if you have a weight within a language model, the way that's stored is in 3 parts that are jammed together. And those parts represent the sign bit, which just says, is it positive or negative? This is a positive number, but if you want to represent negative numbers too, you need a bit that will say it's positive or negative. Then you'll have the mantissa, which is this front precision, and the exponent, as I said, represents the range. So let's look at some common data types that are used in computers. One of the most common is float 32. It has 1 sign bit, 23 mantissa bits. So it's got like this massive precision at the front. And then it's got 8 exponent bits to capture the range. Now the second most common, perhaps, is float 16 here on the 3rd row, which is 1 sign bit, 10 mantissa bits, and 5 exponent bits. So compared to float 32, it's got less precision on the front end, and it's also got less range. So one idea that machine learning engineers came up with is, why don't we create a data type that, big brain idea, why don't we come up with a data type that has the same range, but just trade off the precision up front? And the motivation is that actually the range can be more important to capture in language model weights, because you see very wide ranges. And actually, whether you have like 7 bits of precision or 23 doesn't really affect the quality of the model overall. And because this was a big brain idea, okay, I'm making this up, they called it brain float. It is called brain float, bfloat 16. And this is a data type you'll see in GPUs. Nvidia GPUs have it after the T4, so after the Turing architecture with Ampere, Hopper, like an A100 and A6000, a H100, a B100, they'll all support brain float 16. So because the exponent bits are the same in these two data types, the quality of precision that these models achieve is typically very similar. It's basically excellent. Now, I'm not saying that float 16 is bad quality. Usually float 16, if you use that for inference, it will give you very good quality as well. Moving down the ladder, we get to an 8-bit data type, which is called FP8. FP8 can actually take two forms, but the form I'll show you here, I can take probably more forms, two common forms. The form I'll show you here is E5M2. It's 5 exponent bits and 2 mantissa bits and 1 sign bit. So you can see that FP8 with E5M2 is matching the exponent bits of float 16, and it's trading off a lot on the accuracy of the upfront. Because it has the same range as float 16, the performance in terms of perplexity or quality of the answer, if you use 8 bits, is also very, very good. And so I've highlighted here in green all these data types. They provide very good quality in inference. Now, when you move below this, and it's not like there's a step change, but just it's helpful to draw some boundary. If you go down to 4-bit formats, you do see a degradation in terms of the quality. At the bottom here, I have int4. This is simply an integer, so it has no sign bit and it has no exponent bits. It's using all 4 bits to represent numbers from 0 up to 15. And the way you would even use this to represent a weight is you have your scale of 0 to 15, you have your original 16-bit number, and you will save a scaling factor that will map this large number onto this reduced scale. And by using the same scaling factor across many weights in your model, you're basically able to store, albeit in much rougher precision, you're able to store all these 16-bit numbers now in 4 bits, roughly cutting your storage in 4. So this int4 format allows for a lot less megabytes or gigabytes to be used for storing your model's weights, or you to use much smaller GPUs with less VRAM. But the trade-off is that the precision is a lot more rough, and so you definitely see some quality trade-offs. Now I'll just make some quick comments on these other two data types. There's FP4. This is a floating point 4 data type. It uses 1 sign bit, a mantissa bit, and 2 exponent bits. I have not done a lot of experiments, and by I have not done a lot, I mean I have not done any experiments. So I don't know what the quality of FP4 is. I suspect similar to models that are running int4, maybe a little bit better. I'm not quite sure. There's another data type called NF4. This is normal float 4. You'll have come across it if you use bits and bytes quantization, which is used a lot with unsloth and also transformers if you're trying to reduce your memory requirements. Normal float 4, what it does is define a scale from -1 to 1, and it will break that into 16 different markings that are separated according to a bell curve. So you'll see this normal distribution of points between the -1 and 1. And what you do is you map the 16-bit numbers onto this scale of -1 to +1. And it turns out that actually weights tend to be more normally distributed than uniformly distributed. And therefore, using this normal float data type gives you better perplexity and better quality of answers than just using int4 or possibly FP4, although I don't know a lot empirically about how that performs. Unfortunately, NF4 is not very well supported, as we'll see later in the computation kernels that are set up for GPUs. So it's quite a slow data format, and we will not be using it for inference. You can use it. It is supported by text-generation-inference, but it's got trade-offs in terms of speed versus other approaches. That was quality and quantization. So here we'll talk a bit about speed. Speed is going to depend also on compute type. And I don't just mean the format in which the model is stored. So I don't just mean if the weights are stored in 32 bits or 4 bits. I mean as well whether the GPU is capable of multiplying 4 bits or capable of multiplying 16 bits or 32 bits. So I'll talk a bit about that and what different GPUs support. Then I'll talk about the notion of bandwidth versus model size. This relates to reading the weights from the VRAM. So once they're already on the GPU, into the deep calculating part of the GPU, that's called the SRAM. And I'll also talk a bit about kernel type design and GPU utilization, because these are also important for influencing speed. So let's start off with compute type, and by saying that in principle, if you use smaller data types, you should be able to save time in computation, because multiplying, in principle, two 4-bit numbers should be faster than multiplying two 16-bit or two 32-bit. So it should be good if we can use smaller data types, setting aside the fact that we're trading off on quality. However, we can't even do that in a lot of cases, because many GPUs don't support multiplying 4x4 bits or 8x8 bits. I've got a map here of different GPUs and different data types. And what you can see here in the boxes are the rates of calculation that the GPUs do deep inside their memory, inside the SRAM. And as you move to the side here, to the right, or maybe it's your left, I'm not sure, you're seeing us move towards more modern generations of computers that can do more calculations, more teraflops, which is floating point operations per second. So that's how many multiplications can be done per second within the GPU, assuming that full utilization. So unsurprisingly, as you move towards later generations like the H100 or B100, you can do more calculations. And not only can you do more calculations, but the GPUs are supporting now these smaller data types. And you can see that this allows for faster speed. So in 16 bits here on the B100, you can do 1750 teraflops. But then if you go to 8 bits, you can do double that. And if you do 4 bits, you can do double that again. And that matches the intuition that multiplying to 4-bit numbers should take about half the effort as multiplying an 8-bit number. Now, what you can see in the earlier generations is that there is no way deep in the GPU to do any of these smaller data type multiplications. Now, technically, if you look at the spec sheets, I think it's possible to do in-4 calculations on some of these GPUs, but it's not something that's supported by the software that does language model inference. So for practical purposes, the older GPUs are basically restricted to 32-bit and 16-bit formats, whereas the more recent GPUs are able to do these smaller data formats, and that allows them to get significant speed up. Just one quick comment here, you'll see BrainFloat 16 appear, and I commented earlier on how this achieves the same exponent bits as float 32. And that's nice because it gives the same range, which gives the same overall perplexity roughly. And that's why this has started to be supported as you move towards the more recent GPUs. Now, I've put in the Mac here. These numbers are not really apples to apples with Nvidia GPUs. And the Mac has got a different GPU architecture compared to GPUs like Nvidia. But I just wanted to show that it's kind of in the ballpark of GPUs, and that's why you're able to get very good inference speeds on Macs compared to, say, some of the Windows PCs, the older Windows PCs. So the general takeaway from this slide here is that with the more modern PCs, we're able to take more speed. So we're able to take more speed, trading it off for less accuracy by moving to these smaller data types. But we have this, as of yet in this presentation, unsolved problem that we would like to use some of the smaller data types, particularly the 8-bit one, which is good quality. We would like to be able to leverage that to get higher speed while maintaining quality, but we've a problem that it's not supported down in this part of the chart. And there are some kind of fixes and tricks to get around this that I'll talk about a bit later. Next, let's talk about bandwidth versus model size. So in a GPU, if you massively oversimplify, you have the VRAM, which is where you load the model. So if you have a 70 gigabyte 8-bit Llama model, a Llama 70B model, then you'd have to load 70 gigabytes of weights into the VRAM here, or 140 gigabytes if it's in 16-bit, because there's 8 bits per byte. So that would be 70 billion parameters, would be 2 bytes per parameter and 140 gigabytes roughly. So here's where you have to load the model. But where the computation happens in a GPU is in a much smaller part of the GPU that's usually only 50 megabytes or 120 megabytes in size. So actually the full weights are not going to fit deep where the calculations happen. So what happens when you do a forward pass or backward pass through a model is you actually only handle a small portion of the weights at the one time, and you read those in along with the input tokens or the input tokens to a given layer, and you do the calculations and write that information back. So there are basically two ways that you can get limited on speed when you're running a GPU. The first is that you want to run a ton of calculations and your computer is not able to calculate fast enough. And this is where you're compute limited. But you can also have a GPU that is able to compute extremely fast, so fast that the bottleneck becomes how fast you can read in portions of the model weights from the VRAM into the SRAM. And this is the bandwidth limit. And this bandwidth limit becomes more relevant if you have a large model relative to the size of your GPU. You just become limited in how fast you're able to read weights deep into the VRAM, rather deep into the SRAM. So I've shown here an approximation for the bandwidth of these different models. And bandwidth is measured in terabytes per second. That's how fast you can kind of read into the deep part where calculations happen. And I don't have full data here, but generally the bandwidth is improving as we have newer generations of GPUs. They have higher flops and they have higher bandwidth. Actually, because the flops are improving both on the dimension of just raw compute, but also because smaller data types are being supported, it's actually hard to keep up that rate of improvement with the bandwidth. And so bandwidth is kind of becoming more of a constraint on the inference speed of these models than the raw compute that's possible. So you can see here that, yeah, as you have more modern GPUs, you have more bandwidth and you can read in the weights faster. So in principle, if you can have 4-bit weights, this also will help not just with the reducing the VRAM you need, so you can use a smaller GPU, but it should also make the bandwidth limit less important because you now need to read less data from the VRAM into the SRAM. So yeah, having like 8 bits or 4 bits, that should be a good idea versus having a 32-bit or a 16-bit model just because you're going to have to read less data into the SRAM. The problem is, and this is not a problem if you're on a GPU that supports these small data types. So if you're on a H100 that supports 8 bits, no problem. You can read in 8 bits and do the compute. If you're on a Blackwell 100, you can read in the 4 bits and do the compute. But if you're on any of these GPUs, yeah, you can quantize to 4 bits, but you're not going to be able to compute in 4 bits because the software that's been written does not support doing that kind of compute. So what you have to do instead is a little hacky, and you have to de-quantize. So basically you read in the 4 bits, then you rescale them back up to 16 bits and do your calculation then. Now this sounds a bit silly because you're just undoing the quantization, but it can make some sense because A, you still have a smaller GPU because you need less VRAM. So that might be good if you're running locally. And B, it still can reduce your bandwidth limit, which might be the constraint on your inference performance. So it still might counterintuitively make sense to use quantized weights and then de-quantize them just when you do the compute. And that's roughly what this looks like. You read them in, you de-quantize, and then you do the compute. Now, the problem with this is it takes extra calculation to do that rescaling. And that may not be an issue if you've got a batch size of 1. If you're just sending in one input sequence, probably you're not using all of the calculating power of the deep SRAM. So you can just use some of the excess calculating power to do the de-quantization, and you might not even see a slowdown. But if you put in a big batch of input tokens, so imagine a big batch of input tokens coming in here, you need to crunch a lot of numbers to process all 64, let's say, of those inputs. And now you don't really have much compute to spare. And the extra compute you need to do for de-quantization is now going to slow you down. So a problem with these approaches where you're using, say, 4 bits on a computer that doesn't support 4-bit multiplication is that at larger batch sizes, it's really going to slow things down for you. So this is why generally 16-bit, especially at large batch size, is going to give you the fastest inference if your GPU does not support FP8 or FP4. So if you have an older GPU, yeah, 16-bit with large batch size is generally going to be the fastest way to do inference, but you can use these quantized data formats to save VRAM, and potentially you might even get some speed up if there's spare compute because you're running at a small batch size. Now, there's one further, or rather many further tricks that actually improve on this by another step. And the way that you get around the drawback of this extra de-quantization is you build some custom kernels, and you also think carefully about how to schedule which cores are being used in the GPU. And I know I'm just giving a high-level explanation of how that works, but this is basically how things like AWQ, Marlin, and a lot of work by Neural Magic work. What they do is they combine the step of de-quantizing with the step of matrix multiplication. And yeah, they design some software to carefully assign the operations across the GPU so that everything is being used if possible. And this can greatly reduce the drawback of doing the de-quantization to the extent that you don't even see too much slowdown in this de-quantization step needed before doing the compute in 16 bits. And that's basically the unlock for being able to use these older GPUs, but actually use them with these quantized formats here. So this is my summary chart of recommendations on what to use for quality and speed. And if you just think back to what we talked about on quality, everything above 8 bits is good quality. And if you think about speed, everything 8 bits and lower is going to be good on speed. So there's kind of this sweet spot where you're at 8 bits and you get good quality and you get good speed. And then if you want to degrade quality a little bit, but get some more speed, you can look at doing the int4 type approach. So just a few quick comments here. On the B100, it natively supports 8-bit and 4-bit calculations. So here you can really get great speed and you can get great quality at 8 bits or compromise on quality a bit by going on 4 bits. On the H100, it supports natively 8-bit calculations, so you can get great quality and speed on 8 bits. And you can run the 4-bit if you want to reduce your VRAM requirements. Now for these 3 GPUs here, which are definitely a lot cheaper, particularly the A40, you're able to get good quality by using 8 bits, and you can leverage these. I'm just calling them Marlin kernels, but you can leverage these ideas of custom designed de-quantization and matrix multiplication kernels to get very good speed. And you can get very good speed at the int4 level if you trade off quality. But just remember that on all of these GPUs, you're not natively multiplying in 4 bits or 8 bits. You're de-quantizing. It's just that you're de-quantizing efficiently. Now, if you're running on a Mac, you're going to run in 16 bits. You could use GGUF. You could probably run in 8 bits or even 6 bits. And if you want to get maybe more speed, you can move down towards 4 or 5 bit. And I'll just emphasize that, yeah, I'm not necessarily sure you will always get better speed by going down to lower bits here. It depends also on your batch size, because there is this de-quantization matter. And there's the question of how efficiently those kernels are designed as to whether that slows down your inference rather than actually speeds it up. And with that pile of explanation, we're ready to move on to Inference Software. And I'm going to compare 4 suites. You may have heard of some of these. vLLM, very popular. It's an open source initiative. SGLang is developed by LMSys, which is the same company that does the ERRATA for comparing chatbots or comparing language models. Nvidia NIM, that's private software. I've got a 90-day free trial, and I think I'd have to pay after that, and I'm not sure what the price is. But anyway, you can just see how the performance is in this video. And then TGI, text-generation-inference, which is a Hugging Face library. Now, all of these allow you to expose endpoints that are OpenAI style. I think technically the SGLang one is, I'm not sure if it's technically OpenAI style, but yeah, basically all the parameters are like OpenAI, so it served the purpose very well. And to keep things apples to apples, I'm going to run the same model, so Llama 3.1, the 8 billion model. I'll run some bigger models later, and I'm going to run it in FP8, and I'm going to use an 1 times H100 SXM. So this is the most modern GPU I can get access to. I mean, maybe if I really tried, I could get a B100. You'll remember from the earlier slides that the H100 does support 8-bit multiplications natively, as opposed to these 3, which do not. So we're going to be getting hopefully very good performance. And I'm going to test them in the same way by asking this prompt here, write a long essay on the topic of Spring. It's actually 20 input tokens for the Llama model. And I'm going to restrict the response to 50 token cap. So it'll basically give a response that's longer than 500, but actually it won't because I'll just stop generation at 500 tokens. And I'll use that to measure the tokens that are generated per second. And then we can do a comparison of all of those. So the way I'm going to run these is by heading over to Trelis Research one-click LLMs. I'll put the link below. And this repo here has got a variety of one-click templates. And it's got templates for RunPod. It's got templates for Vast AI. It has some templates for running Llama CPP servers. And it has some tips around choosing different GPUs. So I'm going to want to compare these different libraries. So I'm going to find a template for one of each. And I'm going to find the Llama Instruct 8B one. So here, let's see this one. So here I've got my template, and if you're using RunPod for the first time, you can set up an account. There is an affiliate link here that you can use to support the channel. That will pay a commission to Trelis. And now I'm going to choose a GPU. I said I would pick a H100, and here I have the template set up. So let's take a quick look. We have the Docker image specified here, and then we have the onStart command. Notice that I'm downloading a model, an 8B model from New Research. It's the same as the Meta Llama one, but just isn't gated, so I don't need to add a token. I've specified the context length, the host of zeros, the port, and quantization to FP8. So we're pretty much ready to go here. And this will run, by the way, if you're using an A40 or an A100 or an A6000. But there's one improvement I can make if I'm running on a H100, which natively supports the FP8 content, multiplications rather. And I can read about that in this little README. And it basically says I can use this model here, which is a raw FP8 model, if I'm using the H100. So actually I'm going to swap out this. It's a 16-bit model here that would be quantized. I'm going to swap it out with a raw FP8 model, which will speed my downloads. And it will also natively multiply in FP8. I don't need to specify quantization because the model is already quantized. So let's set those overrides and we'll get the GPU running. Next, that was SGLang. So let's scroll down and find a template for vLLM. So here we have the Llama 3 Instruct template from vLLM. And again, I'm going to pick H100 and I'm going to inspect my, my template. I'm using the vLLM OpenAI Docker template. My model here is the neural magic model, and I've specified a max model length, and I've specified the port here. Now I've also specified HF hub enable HF transfer. I'm not sure if this is turned on by default. It allows for Rust download of weights, which is a lot faster. Now vLLM should support this 8-bit model. It should support it even if I'm using an A40 or an A100. So this is a bit different than the SGLang template where I needed to use the 16-bit model if I was using an Ampere architecture like an A100 or A6000. So a little bit simpler here. You can use this model no matter what GPU you're using. It will use native FP8 if you're using a H100. Otherwise, it will use the smart de-quantization. So let's get that running. By the way, you don't need quite so much gigabytes there because it's FP8 8 billion. That's going to be about 8 gigabytes of weights. So we'll set the overrides and we'll deploy that. Next, I'm going to run the TGI template. So here we have TGI for Llama 3.18b. So again, I'm going to pick the H100 and take a quick look at the template. The model ID, I am going to download the 16-bit one and tell TGI to quantize it in FP8. The port is different for TGI. It's 8080. It's not 8000, so we have to hit a slightly different endpoint. And I've got a max sequence length. I can change that to, I guess it would 8132. Have I got that right? That number doesn't look right. 96. 8192. And Yeah, that actually needs to be smaller than this, so 4096. And its prefill needs to be like this. So yeah, it would have been fine leaving the values I had either way. That volume is probably a bit too large. You can run at just 10 gigabytes and that would be fine. I have set the HF hub enable HF transfer to 1 so that we get fast downloads, and we will deploy. Next, I'm going to deploy the final interface, which is the Nvidia NIM. So let's see if we can find Nvidia NIM. And actually, it looks like I don't have the Nvidia NIM template set up here just yet. So I can do that now just by editing. Next, we're going to set up Nvidia NIM. So I'll scroll down and find that template. Just a note that if you run the 7dB, you do need to run it on 4x H100. And if you try and do it on 2, it won't support it. And I don't think it will support it on any other GPU types either. So you'll need to run the 7dB on the H100s. At least for now. There could be new support that emerges. So for Nvidia, I'm going to pick again the H100 and take a check at the template. As I said before, this is private software, so you need to sign up for some kind of a trial. There's no container start command. And notice also that the container is specific to the model. It's not a generic endpoint where you specify the model like all of the others, SGLang, TGI, and vLLM. So here we have the 8B. I'm leaving 20 gigabytes in case it's going to download a 16-bit model. And there are a few other tweaks I need to make on this. So let's look at the instructions. I think you can run on an A100 or H100. And there are a few added variables. So I need to add an API key. So you'll need to get your API key for NIM. And not only that, I need to add credentials for getting the image. So the image is not open source. So once I start up the pod, it's not going to be able to get this image without me putting in container credentials. As I said, I also need to set this NGC API key. And I need to set that to the value of my API key. I've saved it in my secrets. So I'm just going to use it right here. So you'd have to either just input the value of that key or save a secret within runpod. So I'll set the overrides and deploy. And when I go to my pods, this is a bit different for the Nvidia pod. I need to go to edit pod. You see it's unauthorized to get that image. So I'm going to edit the pod and I need to set my container registry credentials. So I've saved my registry credentials in my profile for runpod. It's basically passing in a password and a username. So that's pretty much how I've set it, and I can click save. And now it should be able to access, it's able to access the container now because I've set my credentials. So let's check on how all these pods are running. You can see the SGLang one is fired up and ready to roll. We love the language. vLLM, this one here, is also fired up. And TGI, it looks like I ran out of space on the TGI model. And that is because TGI is downloading a 16-bit model. So I wasn't thinking straight there. It's going to download 16 bits and then quantize. So I need to adjust that to 20 bits, 20 gigabytes. And this model here is still extracting. So what I'm going to do now while they're all starting is start to move to my inference tests. And I'm going to use the advanced inference repo from Trelis. This is a repo that contains a lot of scripts from prior videos. It's a private repo describing how to set up servers with runpod, VastAI, Llama CPP, serverless. And it also contains a wide variety of API calls, including zero-shot function calling, which is now my recommended way to do function calling, simple API calls to measure speed, data extraction using structured outputs. And then there are other techniques, including data extraction or anonymization prior to sending into LLMs, and also Monte Carlo techniques. So this is a repo you can buy lifetime access to if you go over to Trelis, trelis.com. And what I'm going to use is the API call section. So I'm going to git clone this over to my VS Code and we'll take a look at it there. So I'm in Advanced Inference now, and I'm going to work out of the API calls folder and the speed test folder. When I'm running this, I'm going to use a virtual environment, and I'll have set up API env. So I'm just going to source API env and activate the API env environment. First, I need to be in the API calls directory. So I've activated that, and I'm going to cd into the speed tests folder. And now I'm ready to run a script that's going to test the speed, and it's called vLLM speed.py. This is my simple single batch test. It just hits an OpenAI endpoint. So even though it's called vLLM, you can hit any OpenAI style endpoint. And it asks a question here: write a long essay on the topic of Spring. And it will limit the output of the chat to 500 tokens, and it will measure the time for response. So in order for this to work, I need to set the endpoint that I'm going to hit, which means setting the run pod ID and also setting the model name. The model that I'm going to run, it will actually depend on which template I'm going to hit. So let's head over to the pods, close all of these other screens here. And we'll start off with SGLang, which should be up and running. So I've got my pod ID, and I know using SGLang, I'm using the Neural Magic Instruct model. So let's save both of those, and we'll run Python vLLM speed. And you can see 154 tokens per second. Now, the other test I'm going to run is running in parallel. So this is my speed concurrent script. And what this does is it will send 64 requests, and it will send them at a spacing of 61 milliseconds. So I'm actually, this is a nuance, but I'm actually not just sending in a batch. I'm sending them in spaced with these tiny increments. And my reason for doing that is I want to test how the scheduler is actually handling different requests coming in at different times. If you just send in one batch, you could programmatically handle that more easily. So this, I think, is a little bit better of a test of how well the server is able to deal with a more realistic, I'm not saying it's perfectly realistic, but a more realistic load, a more realistic workload. So to run this script, I'll run Python vLLM speed concurrent.py, and it's going to send in those requests, and you can see they're all coming back now. And what's remarkable about SGLang here is, like, we're getting about, for each request, this is each single request, we're getting about 142 tokens per second, which is not really far off the single request value of 160. So SGLang is really performing well here. Now we'll work our way up and take a look at a vLLM. So here I need to grab my pod ID and input that into my environment variables. And with vLLM, I think I'm also running this same model. I'm just going to unset the API endpoint to make sure that we're not accidentally hitting the same server. And we'll run the vLLM speed test. So 117. So you can see vLLM is doing pretty well, 130 versus 160 for SGLang. So pretty good performance from vLLM, at least on the single request. And now we'll test out the concurrent requests. And what we'll see here is that vLLM is a bit slower. So the scheduler is not performing as well. You can see the tokens are down now around 40, 41, 23. So definitely slower. Next, we'll move on to TGI, and let's take a look. Everything is up and running fine. And we're going to be hitting this pod ID. So let's grab that, head over to VS Code. And we actually downloaded the model in 16 bits, and then we specified quantization. So I need to change the model to this one here. I'll unset my API endpoint and also the model. And now I can run the speed test. And it looks like we have not found that endpoint. And you know why? Because we are hitting a different endpoint for TGI. It's the 8080 endpoint. So for TGI, I need to use an 8080 endpoint, and I'm going to use this model here. So if we unset and run, By the way, you can run TGI with an OpenAI style endpoint. I'm running the exact same script. And you can see here it's got 112 tokens per second, 120. So maybe a tiny bit lower than vLLM. Let's see how it does on the concurrent test. And yeah, you can see here that TGI is definitely faster than vLLM. It's achieving about 73 tokens per second versus 40 on the concurrent test. So better at scheduling, but definitely not as good as SGLang. And last of all, we have this Nvidia NIM test. Let's see if we're up and running. It looks like it is. So I'm going to grab this, this ID here. And I'm going to go right back up to the top of my script. I'll comment this out first and change the run pod ID and select the correct model here. Now, I'm not sure if I have, is it the Neural Magic one? No, it's not. It actually needs to specifically be this model here, which is the Nvidia named model. And I have that listed right down here. So with that, I'll unset again my API endpoint and model and run the script for the speed test. And here I'm not getting the right model name. And so I'm just going to go back and check the logs. There's a sample curl request here and it has the name of the model. And indeed, I actually was using Llama 3 instead of 3.1. So that needs to be replaced. And I'll unset again and I'll run the script. And it should find the model now and give us the time for 1 token of inference, or rather 1 prompt, 1 batch size. And we've got 61 tokens per second. So 140. Often the first request is a bit slower, but yeah, 140 tokens per second, 132. So this is up at the vLLM level. It's not quite getting the inference speed of SGLang, but pretty good. And let's take a look at the concurrent and see how that compares. So here we're hitting it with those 64 requests that are spaced by about 61 milliseconds each. And it's somewhat arbitrary, that spacing I use. So 118. So this is achieving better concurrent performance than TGI, but not quite as good as SGLang. But before I go to look at comparing GPUs, let's take a recap of our results. So with a batch size of 1, we have SGLang, which is leading roughly 160 tokens per second on each of the batches. Well, this is batch size 1. You can see NIM is pretty good. I mean, they're all pretty good, to be honest, in terms of speed, but SGLang is the fastest. And yeah, I may be a bit surprised just that NIM is not, because that is the Nvidia one. So I would have guessed that would be the highest performance. When it comes to larger batch sizes, then there's more of a divergence in performance. SGLang and NIM are performing very well, but we're not seeing the same rate of token generation from vLLM TGI. And you can see here I've compared, actually not shown in this video, but I compared running TGI in both FP8, that's with the FP8 selected, and also in BF16. And I didn't really see much difference in performance between these two here. And for the final part of the video before the last tips, let's talk a bit about comparing the costs. And we're going to compare a few different GPUs. The A40, I won't bother with the A6000 here, but I'll show you the results. The A100 and the H100. And we're going to compare them for apples to apples, all with SGLang, all using FP8, although the FP8 will obviously be native on the H100 and it will be de-quantized on the A40 and A100. And we'll use the same model, the 8B. And I'll actually talk a little bit about then the 70B model and also the 405B Llama model, which is a lot larger. So let's get some GPUs started for A40 and A100. And I'm going to do this by going to SGLang. And let's try and find templates for that. Okay, here we go. So we want to use the FP8. And we'll want to select this time an A100. You could pick a PCI rather than the SXM. And I think that would be a bit cheaper. Is there actually? Yeah, this one here is a little bit cheaper, but I'll just go with this for now. And let's check out the template. So yeah, for SGLang, we're not gonna load the Neural Magic model is not loading via SGLang. It does with vLLM, so I'm gonna have to just load the 16-bit and then have it quantized by SGLang. So here, if we're loading that 16-bit, we actually need to have a bit more VRAM. So I'm going to put in 20 gigabytes of VRAM to make sure that this all goes fine. And we will click on deploy. And then we'll do that one more time for the A40. Oops. So here I'm going to select an A40, which is 35 cents an hour. It's the cheapest one. And we will again leave this as is, increase the space a little bit, and set the overrides and deploy. So with that, we can take a look at our GPUs. I have the H100 already up and running, and we've already measured the inference speed there. It's about 160 tokens per second for batch size 1 and about 130 tokens per second when we move batch size up towards 64. While we're waiting on the 8B models to boot up, let's take a quick look at how we would deploy 70B and 405B. These are larger models, so you need to run multiple GPUs. My recommendation for high quality is to try and target an FP8 format. You can do that on two A40s for good value, or you can run with two H100s. If you run with two H100s, you can swap in the Neural Magic pre-quantized 8-bit model for faster downloads and inference. So I'll just show you how to run this 4x840, but I actually want to show you using the int4 format. This is the quantized format if you want to get a bit better value. You could actually run it on just two A40s, but the inference will be quite slow. So what I just want to show for the purpose of demonstrating the int4 is I'll boot up an int4 template. Let's just look for SGLang, and let's grab the 70B int4. And instead of running it on two A40s, which will give low tokens per second, I'm going to run it on four A40s, and we can just inspect the template. Tensor parallel size needs to be adjusted to 4 if we're running on 4. You can run on 2, it's just that it'll be slow. And we're using the Hugging Quants model here. It's going to be 70 divided by 2, roughly 35 gigabytes. So 50 gigabytes should be fine. And we're off to the races there. Now, if you're going to run on a 405B model, you can run this on 8 H100s. That's expensive. That's going to be like 4 8s, $32 per hour. And you can do that with SGLang. If you want to compromise a bit on quality, you can run it in the int4 format, and you can do that on 4 H100s. Now, I will just show you some of my results. You can try running this on an A100 or an A40. You could run on 8 A40s with the quantized form. Unfortunately, you can't run the full FP8 because you would need 16 A40s. It has to be multiples of 4. You can't just do 10. So you're not really able to run FP8 on the cheaper GPUs. You can run int4 on 8 A40s, but the inference is going to be pretty slow, as you'll see in some of the results that I'll show. So let me just get something moving here. I'll try run the int4 on 4 H100s. So let's go over to SGLang. We'll find the int4 template here. Pick the 4 H100s and just check. Tensor parallel size is going to be 4, and then we're running the int4 model. So with that, we can set overrides and deploy the pod. So here now, I can go back to my pods. I'll close the other tabs, and let's check out what we have. So we first of all have the H100, which we've already run. That was the 8B model. So we know that's 160 TOCs and 130 for the batch 64. We're now interested in checking out how fast the model will be if it's run on an A100 instead of a H100. So it looks like this server here is fired up and ready to roll. So we can go back across to VS Code and run on the A100. We're going to be using the new research version of the model here. So I'll save that, unset my environment variables, and run the speed test. And remember, this is an A100, single A100 on 8B. We're trying to compare costs. So about 100 tokens per second from this model with the A100, maybe 116. So there's going to be variance. And then with the concurrent test, let's see, we're using SGLang, of course, for all of this. We're using SGLang for all of this, and you can see, yeah, we're getting about 80 tokens per second here on concurrent. Now we can compare the cheaper GPU, which is the A40. So let's see how that does by comparison. So all I need to do is swap in this pod ID. So we're comparing 80 here for the A100, whereas on the H100 we got 130 with SGLang. And let's see now if we unset what kind of performance we get in the concurrent test using the A40, which is by far a cheaper GPU. So we're expecting something less than the 80 tokens per second on the concurrent. I can't remember, maybe about 40 or 50 is what we should see here. So I'll just run a single token test on the A40 model and see how that does. And we're getting 52 tokens per second. That's compared to about 120 using the A100. So we're definitely getting slower inference here on the A40. And let's look at the concurrent test, see what kind of speeds we get with batch size of 64 with kind of increments in that 61 millisecond gap between the requests. And it looks like we're getting about 43 in terms of speed. So if we take that data and we take a look at the inference all in a Sheets document. So I have this Sheets document summarizing the results. We can take a look at GPU pricing for the Llama 8B. And here I'm looking at the speed for doing batch sizes of 64. And you can see a variety of options. So the ones we ran here were the H100 doing 130. We ran the A100 doing about 100 to 120. And we ran the A40, which was doing about 40 here. Now I also ran the A6000 and I ran the A40 in int4 format just to see the comparison. And when you do the maths out here with the dollars per hour and you calculate what is the cost per million output tokens, which is simply the hours run or the dollars per hour divided by the tokens, divided by 3,600, adjusted for per million tokens, and then divided by, that's pretty much it. That's the calculation. You get the cost here. And the cheapest, by a fairly significant margin, is to do inference on the A40. What you'll notice is that it's not really much cheaper to do int4. There's a tiny bit higher speed in the token generation, but not really much. And you're going to degrade quality. So my recommendation is to keep it in FP8 if you're going to do inference, because that gives you the best quality versus speed trade-off. Now we can take a look at some inference on the 70B and 405B models. Okay, so by now we have loaded up the 70B and 405B models. I'm just demoing the int4 formats. I recommend FP8 if you want higher quality. So we'll take a look first at the 405B model. It's just loading the shards, so almost ready. And here we'll take a look at the 70B model, which looks like the shards have just been downloaded. So that is now capturing the coup de graph. This means it's basically setting up an algorithm to run the forward pass in a more efficient way. This takes a little bit more GPU memory, more VRAM requirement, but does result in faster inference. So it looks like we're up and ready now with this 70B server, 4 times A40. So let's head back to VS Code, plug that in here, and now select the 70B model, which is actually the Hugging Quant one because we're using int4. I'll clear my API keys and let's take a quick look at the speed test. So tokens per second on batch size 1. And here we have about 33, 34 tokens per second. I'll just run that again because often the first request can be a little bit slower for some reason. Okay, so 37 tokens per second. And let's get the concurrent test running. And in the meantime, I'm going to back over to my costing spreadsheet. I haven't run this test before with four servers using int4. I'm going to put in set 37. I'm just keeping track of my batch size 1 inference time over here. But really what I care about is my batch 64 performance. So let's take a look. And it looks like it's still running. I'm expecting it could be fairly slow. My cost per server here is 35 cents. And you can see how exactly I calculate this cost per token. So I have 4 servers, times the 35 cents. And then I'm dividing by the tokens per second, the seconds per hour. And here I've got the batch size 64, because I'm generating 64 batches, and then per 1 million tokens. So all I need now is to input the information here. So about 17 tokens per second on the concurrent. So you can see that actually I didn't really increase. I increased my speed marginally by going to bigger GPUs. So I didn't really get a big benefit from going to 4 GPUs. But I did manage to take my cost down a tiny bit, just because this is helping with bandwidth. So more GPUs is helping me out here. Now I've run a variety of tests here on Int4 with 2 A40s. I've run FP8 on 2 A40s, but ran out of memory. And I ran on 4 A40s, and that ran fine. And then I ran on an A100 and also on different numbers of H100. And there are a few interesting things here to note. The first is, in terms of price, if you want to get a low price, you can use the A40s, and that will give you the lowest price. Int4 will give you the lowest price of all, although you're trading off on quality. Now, one of the issues, though, with using these cheaper GPUs is that the tokens per second that your customers will get are quite poor. Like when you're down at 16, 17 tokens per second, I know it's a large batch size, but still that's kind of slow experience for customers. So if you want to get better tokens per second, that's where you're kind of forced to using more GPUs. You could also try out 2 A100s. I tried out 2 H100s and 4 H100s, and you can get up to some very nice inference speeds, albeit at increased costs. Now, what's interesting here is there is kind of a local minimum, and I would want to do more work to validate this, but it seems that moving from 1 H100 to 2 will get you down in terms of cost because the output goes up. It seems like for this 70B model, I'm just constrained on 1 GPU, and I get a very big increase in token generation rate with 2 GPUs. But then if I go up to 4 GPUs, my cost per token goes down, presumably because bandwidth to move between GPUs is now becoming my constraint, although I would want to think through that a bit more carefully. The last category I want to look at is the Llama 405B set of models. And sorry, I should have increased my screen size a bit before now. But here I've set up 8 by A40. And actually, you know what? I've just realized that experiment I set up. Let's see. Is it going to be a new experiment? It's corresponding to, a new experiment here where I can just put in 4x H100 XSM, and we're running an int 4. So let's take a look at how this will perform. We'll move over to VS Code, and we're now running the 405B model. So let's unset the environment variables and run a speed test on the 405B model using SGLang. And I've got 4 H100s. So let's see how that does in terms of performance. 36. So do a quick second test. That's pretty good though. 36 tokens per second is definitely not bad from a user experience standpoint. So we'll see if it goes up a little bit more when I run it that second time. 37, and let's run the concurrent test. So in my spreadsheet here, I'm just going to mark 37 for a single test. My cost of GPU is $399. And here, if I do the calculation, I've got 4 GPUs times $399 and then divided by 64 divided by tokens per second. And I'm waiting on my rate of token generation. I'm expecting it maybe to be somewhere around 10 to 20. Okay. So about 17 is what I'm getting here. So you can see in Int4 format, I'm able to save some money versus doing FP8, but I'm not saving all that much money. So again, there's kind of a case where because of quality reasons, you may just want to use FP8 if you have heavy loads to get better quality and not really end up paying all that much more. You can indeed save quite a bit of money, like a factor of 2 if you use A40s with the A4 format, but look how slow your inference is in Int4. This is not really great. 5.62 tokens per second is not a speed that your customers will be happy with. So unfortunately, the cheaper hardware is just a bit slow with these larger models. And that's why I probably recommend going with H100s in order to get the best tokens per second experience for your customers. And also, it's really not that much more expensive than using A100s or using H100s with the Int4 format. Now, there's one last comment or set of comments I'll make here, which is comparing these costs to OpenAI. OpenAI and many services will charge on million of input tokens and million of output. So if you consider the prompt that we worked with today, which is 20 tokens of input and 500 tokens of output, and then you convert that to a price on a per output token basis, which is the same basis as here, you can kind of do a comparison. I'm not saying this is exactly right, because in practice, the types of prompt that you will get probably have a lot more input. I don't know, an average of a few thousand tokens of input, and that will skew the comparison. But if you really want to do a comparison on this basis, you can kind of see how GPT-4o Mini, about 60 cents per million output tokens, all in. And it puts it roughly in the range of a 70, somewhere between an 8B and a 70B model in terms of size. So my guess is probably GPT-4o Mini. It's either roughly that size, or if it's an MOE, then one of the experts, or how many experts they're using. If it's 2 experts being chosen, I'm expecting those would roughly be of a size between 7 and 70B. And then if you look at GPT-4o, which is a lot more expensive as a model, it's about 20 times, 23 times the price. You can see that it's actually priced at above what it costs me to inference here. And keeping in mind, OpenAI probably gets servers that maybe half the price is what I can rent them for. So you can imagine this is really probably quite a large model. And of course, there's margin that's been built in there as well. But it just gives you a sense of how some of the top models today probably are in the hundreds of billions of parameters. And that may even be hundreds of billions of parameters just for single experts or groups of selected experts for the inference. And that's now time for final tips. So of all of the inference softwares I've looked at, I think TGI, vLLM, SGLang, and Nvidia NIM, they're all fast for small batch sizes. But as you get to larger batch sizes and a heavier load, you do see differences, and SGLang seems to perform better, as does Nvidia NIM. All of these, I should note, do support structure generation, so you can use any of those rather interchangeably. SGLang probably is the leader, though, in terms of speed, ultimately, whether on small or larger batch sizes. When you're thinking about the data format to use, I would gravitate towards FP8 where possible. It gives you good quality, but also gives you good speed, particularly if you're operating on a H100. And if you really need to skimp on costs by having lower hourly costs, although not necessarily lower token costs, Int4 can be an option if you're willing to trade off a bit on quality. Keep in mind that it's not necessarily obvious that the cheapest GPU will be the best choice, just because using the cheaper and older GPUs will result often in lower tokens per second, and that gives a bad customer experience. So that's why, particularly for larger models, you're kind of forced onto using these more expensive models in order to maintain not just an okay token cost, but an okay inference speed for each individual user. Whereas on the smaller models like the 8B, you can get away with using the cheaper GPUs and achieving both good tokens per second and also good costs per token generated. And that's it for this mega video on inference, the inference showdown. You can check out the materials in the one-click LLMs repo on Trelis on GitHub. That's a free repository. And if you'd like to check out the inference scripts, you can find those on Trelis.com, where you can buy lifetime access, including future updates to that GitHub repo or subsets of the scripts within. All the best, folks. Leave me the comments below if you have any questions. Cheers.